Justin Miller, College Physics here. Hi, how you guys doing? Everybody's doing good? What am I doing? I'm waving. You know why? Because we want to start looking at waves. Traveling waves nonetheless, and traveling sinusoidal waves even nonethelesser. Anyways, this is what we want to start looking at now, is waves. Yeah, you talk about going to the beach and seeing some waves, or sound waves, or radio waves. There's all sorts of different waves out there, but they all exhibit a characteristic that is explainable by some simple phenomena. So let us take a look at some properties of waves in general and discuss what is a wave. Well, a wave is, in general, a disturbance that propagates through a material or across a material, except in the case of electromagnetic radiation, light. Light doesn't need a material to travel through. It travels through free space with an oscillating magnetic field and electric field. So we're not going to be specifically looking at light here. We're going to be looking at other types of waves, water waves, waves on strings, sound waves, and such things. So ultimately, like I said, a wave is just a disturbance that propagates or travels across or through some material. And that's it. So, this is going to come back and hit me in my face here. And I got a little elastic cord here. It's some material, right? I can set up a little disturbance on this. And what it's going to do, it's going to travel across this. It's going to bounce back and go back and forth a couple times. But I just want you to see it. All I do is I push it down a little bit and then release it. And when I get this little disturbance, bounces back and forth. Now how fast it bounces back and forth depends on some characteristics of the actual material that is housing the wave. But nonetheless, that's what it does. Bounces back and forth. Well, that's not the only type of wave. That is known as a transverse wave, where the displacement of the material is perpendicular to the direction that the wave actually travels. So we call that transverse. And then there's also what's known as longitudinal waves. And longitudinal waves, well, the displacement of the material that houses the wave is parallel to the direction that the actual wave is traveling. So these are more like compression waves. But if I take this slinky here and I bunch up a bit of it, bunch up quite a bit, bunch up this little portion right here and let go of it, that little portion is going to travel down as a disturbance, and then it's going to bounce back up. Not bounce all the way up, but it'll undergo some reflection. But watch. We got that this disturbance travels back and forth. So I can kind of go like this and get that disturbance going, or I can start doing transverse type of motion. That doesn't work too good like that. The transverse type of motion, and seeing the transverse aspect of the wave on the slinky, just by going like this, and then I set up a little disturbance, and it goes back and forth, where the motion is transverse or perpendicular to the direction that the wave energy is traveling. So those are the two ends of the spectrum, if you will. With respect to waves, there's all sorts of other complex waves that have both longitudinal and transverse aspect to them simultaneously. Water waves, surface waves across materials. Some of them get really complex. We're going to focus our attention at this point on transverse waves, though it does correlate with longitudinal waves as well. It's a little bit easier to think about transverse waves. So, you got water in your garden and the hose is stuck. What do? You give it a little whip, right? And this pulse kind of travels down the hose and hopefully unlatches from whatever is constricting it. But that's an example of a wave. Now that's just a pulse, really. What we want to be looking at is sustained waves. Waves that just keep on being produced and keep on moving at some finite rate across or through a material. And we want to talk about sinusoidal waves at that. So there's different wave shapes, but we're just going to look at sinusoidal waves that have some nice flow with them. So what we're going to have is, this pin's already giving me problems. All right. These are supposed to be new. All right, let me do this. We will negate that. Try a different color here. Come on, purple. sinusoidal traveling transverse waves. So what we would have is we can draw out some axis here, and we can have this. We can have that we've got this wave, sine wave if you will, right, like this. But it's not this just burned into space. This would be like a snapshot of it at a specific moment in time. What we would have for a traveling wave is that this wave has some wave velocity in a particular direction. In this particular one, I'm putting it going that way. And generally you say that's the positive x direction. The wave energy could be traveling like this, but this would be something where this is advancing in time. This whole thing right here, this whole packet of what I've drawn continues to advance to the right at some finite rate. And as long as it's continuously being produced, it's continuously going up and down. And what we have with this is if we look at any element, any portion of this wave, really what is it doing? If I look at this portion here is just going to be going up and down. This particular, we'll say, mass element of whatever is housing it, we'll say it's a string, is just oscillating up and down. But everything's doing that. Everything's doing that, but out of phase or out of sync with its next door neighbors. And this ultimately produces this wave, traveling wave sort of phenomena here. So what we want to look at is how do we model this? How do we mathematically explain it? And what sort of characteristics can we extract from a traveling wave here? So let's do this. For a traveling wave, we write the displacement of an element of the wave at position x and time t. Traveling wave, we write the displacement time t as y of x and t is equal to, now we need some formal expression. So this is the displacement at position x at times t, and that is equal to a times the sine of kx minus omega t plus phi. There's the expression for a traveling sinusoidal wave. What do we have with this? Well, again, this is the displacement. The displacement is a matter of this, right? We could say we have some position right there, some position x1 at some t1. This would be the displacement y of x1 comma t1. We could have some other position x. Maybe we want, what's the displacement of this position x at that time t? Well, that would be equal to 0. This one would be equal to the maximum value, which would be a, because if this is sinusoidal, it just goes between the maximum displacement, 0, and the maximum displacement in the opposite direction. There's the amplitude of the wave. So this is what we have. What we want to do is explain this expression here a bit and understand some of the characteristics of a traveling wave. All right. So in terms of this picture up here, that would be representative of like a snapshot at some time t1. If this is traveling to the right throughout time, well, that's hard to draw off on the board, right? Because it would be moving and different locations would have different displacements at different times. It'd be very dynamic. Let me show you some some animation of something a little bit later on, but the best that we can do with this is say that this is position X here. We should say that this is like Y of X at a specific T. And that's how we gotta kind of draw things out in 2 dimensions. And this is really, has the time component in it too. Anyways, let's take a look at this. What is A? Well, A is the amplitude of the wave, which is the maximum displacement from its equilibrium position. All right. What else do we have? We've got a K, an X, an omega T, and a phi here. Let's just go down the road, right? K is called, well, you may say, oh, K is a spring constant, right? There's no spring here. There's no spring constant. K is something else in this particular case. Get it? Case? Anyways, K is called the wave number. The wave number has certain units. SI units of radians per meter. Well, yeah, A, we already know amplitude is a distance measured in meters for SI units. So we'll get back to K and say, well, what is that a measurement of? Wave number, radians per meter. We'll get to that. Let's just keep on going. X is the position. That's pretty evident, right? Then we've got omega. Omega is the angular frequency of the wave. And we've talked about angular frequency before with respect to simple harmonic oscillators. And the angular frequency characterizes the number of radians that it sweeps through per second. So we'll just go back with this. SI unit of omega is radians per second. All right. We got a couple more things. T is the time. And lastly, we've got ourselves phi. Phi is the phase constant, which is determined by the initial conditions of the system. Say by the initial state of the system. And depending on what we're going to be doing, phi might be 0, or it might be somewhere between 0 and 2 pi. But it's just so we can start the wave at any sort of positioning with respect to time. We'll get to that later. A lot of times we're just going to say it's 0. This is what we've got. Well, let's go ahead and start figuring out what a couple of these things really are here. And kind of going from there, shall we? Yes, we shall. Throw that up there. And I am going to erase some of this, not all of it. I'm keeping some. Let's see what we can extract. All right, so we said we've got an expression. We've got the displacement of the wave at position x at time t is given by a times the sine of kx minus omega t. And we'll just say that for this particular case, phi is equal to 0. Well, that's important because if phi is equal to 0, if we look at x is equal to 0 and t is equal to 0, at position x equals 0, at time t equals 0, that puts us, well, what's the sine of 0? Minus 0. The sine of 0 is 0. That puts us right here. Right like there. 0 displacement. If that wasn't the case, if we're actually starting time when there is a displacement, non-zero displacement at x equals 0, then we add in some phi here that's non-zero to make sure that that matches our condition. But let's just start it like this. This is what the wave looks like when we start time, and then it keeps on moving to the right with some particular velocity, v. All right, so let us start looking at this a little bit. Let us take a snapshot like this. Say that this is a snapshot at t is equal to 0. So that's what the wave looks like if you took a picture of it right when we're starting time. We're assuming it's already there, this is the position that it's in, and if we advance time, we'd see the wave starting to advance to the right and continuing to be produced. But if we say that a snapshot at t equals 0 is representative of this, what do we have with this? Well, we've got y of x comma 0 is equal to, well, if t is equal to 0, that back end goes to 0, and we've got a times the sine of kx. So this gives us the displacement of the wave at position x, anywhere we want, at t is equal to 0, though, at a specific moment in time. Well, that's great. That's great. So what we can start thinking about is, well, is there anything that we can kind of get out of this kx to understand that k? To understand the k, and the answer is, yeah, definitely. That's what we want to do. We can understand k because we know something about how sine works, right? The sine of 0 is equal to the sine of 2 pi is equal to 0. Every 2 pi radians, this function just repeats itself. It goes through one cycle. So that's it. Sine of kx repeats every 2 pi radians. And by that we mean every time that kx advances by 2 pi radians. So if we're starting at x equals 0 and we want to know, well, what's the next time we're in the same exact state? That'd be right here. 2 pi radians advanced forward spatially. So at, let's say, kx is equal to 2 pi, we have moved forward from x equals 0 by one full cycle of the wave. One full cycle. Well, this is what we want to look at always for cycles, right? Is the repetitive nature of something. How does this wave repeat itself? Well, when we're looking at a snapshot in time, we look at the repetition spatially, the spatial repetition. And if you look closely, if we start here and start there, well, there's one full repetition. Going up, then down, then back to where we started. I come here and keep on going. Hope if this were to keep on going over there, that would be another full repetition. So that's one spatial cycle, and we're going to call that something in particular. So, try this in here. So if we go from here, that is that position right there, and then this position right here, this right here, that distance, this is one full spatial cycle. And we're going to call that something in particular. One full cycle. It's P-A-T-I-A-L-L-Y. One full cycle spatially is called the wavelength of the wave. Which we use this symbol for, Greek symbol, lambda. So, this right here, this distance from there to there, one full spatial cycle of the wave, lambda. So from this, from x equals 0 to kx is equal to 2 pi, that entails one full cycle. Because that's where the sine function starts repeating itself when kx is equal to 2 pi. So from that, we can get that. This one's actually working good. From kx is equal to 2 pi, we can solve this out for x, right? So x is equal to 2 pi over k. Well, if we start at x equals 0, and then we're going to x is equal to 2 pi over k, that is advancing one full cycle. So this is actually lambda here. When x is equal to 2 pi over k, we've advanced the distance lambda from our starting spot, x is equal to 0. So from this, we have the ability to deduce what k actually is. So from this, we can just first write that lambda is equal to 2 pi over k. Again, lambda is the spatial extent of one full cycle. It's a measurement of distance. This has units of meters. And then we can solve this for k. We get that k is equal to 2 pi divided by lambda. That's what k is representative of. It is representative of the number of radians in one full cycle divided by the spatial extent of one full cycle. And that's why we get those units of radians per meter. 2 pi radians per, well, how many meters there are in one full cycle. That's the wave number k. It's a little bit easier to think about the wavelength of the wave, lambda, but it's interwoven within that k right there. So there we go. If we know what k is, we can figure out quite easily what lambda is. Or if we know what lambda is, we can figure out what k is. That's how they're related with one another. All right. So we got something with respect to k, the wave number, and we can also do something similar to that with the omega t part. So now, how could we not take a snapshot, but look at the variance of the wave's displacement through time? And to do that and draw it out in a singular graph, we'd have to pick a point in space. Say, you know what? I want to take this point right here to x equals 0 and see what it does throughout time. So, what do we have to do? Well, in order to see what this point is going to do next, we've got to be able to look back in time, in a sense. What's coming up? We assume that there's sort of this wave still being produced. Not assume, but we can imagine. We can kind of go like this. That this is what's going to be coming in to fill in this spot as this wave moves forward. So what's this point going to do next? Well, this portion's going to move in, and this point's going to go down, and then it's going to go back up, and then it's going to go up here. And this fills in that space. So how do we look at that? Well, again, we can just say, let's look at x equals 0 and see what's going on. Now, look at a set position of x equals 0 and see its displacement through time. So what do we have? Well, if x is equal to 0, we've got y of 0 in t at position 0 through time t is going to be a times the sine of, well, x is equal to 0, so that kx term is 0, and we're just left with negative omega t, which we could write out as being equal to, because sine's an odd function, negative a times the sine of omega t. So you may have asked yourself a question, maybe not, but we'll bring it up now. Why do we have that kx minus omega t? Why isn't it plus? And that has to do explicitly with which way the wave is traveling. Is it traveling in the positive x direction or in the negative x direction? This one we've said is traveling in the positive x direction. In order to see what's coming next, we have to look behind it, behind the point under observation, which is kind of like looking backward in time. That's why there's that negative sign there, minus omega t. If the wave happened to be traveling this way, we would have to look what's on the positive side x-wise to see what's coming next. And, well, in a sense, it's kind of like looking ahead in time, kind of reversed around. But really, this can be plus or minus. Generally, stick with minus, it's traveling to the right. But if it was plus, that'd be traveling to the left. Write that down in a little bit, but this is what we've got. This describes the variance of the displacement of the position x throughout time. At t equals 0, we're at 0. As time goes forward, well, it goes down, and then it goes back up like a negative sign function. And this is what we've got. So this is going to be y of 0 t. This is going to be time axis now. And we're looking at this position x is equal to 0 and what it does throughout time. So what does it do? Well, first it's going to go down, then up, then down, then up, then down, then up. And it's going to have its plus and minus a that it oscillates through. And that's basically that. That's what it does. It goes up and down and up and down and up and down. What could we figure out with this? Well, again, the sign of argument repeats itself every 2 pi radians. So we can identify what is that. Well, if we're starting like this, one full repetition over would be from here to there, right? That would have to be equivalent to omega t is equal to 2 pi radians. And we know that that is one full cycle temporally, or one full cycle in time. That would be, well, the time it takes to complete one full cycle. So this point here goes down, then up, then down. I should say it up there. Goes down, then up, then back to where it was. And omega t is equal to 2 pi, so what do we get? Omega t is equal to 2 pi, which gives us that omega is equal to 2 pi divided by, I'm not just going to put any t, I'm going to put this t. T is the time to complete one full cycle. The period of the wave, which we've looked at with simple harmonic oscillation as well. So it's the same kind of omega is correlated with the period of the wave. So that omega up there is really equivalent to 2 pi divided by the period. It has to do with the temporal extent of the wave, whereas the kx, the k, specifically has to do with the spatial extent of the wave. So that's what we got. So we can always write this again as the period is equal to 2 pi divided by omega. So if you know what the angular frequency of the wave is, you know specifically what the period of the wave is. And furthermore, we can always go back with frequency, right? Frequency f is the inverse of the period, and this is measured in hertz, cycles per second. So it's just like with the simple harmonic oscillator. These are wave properties in general for cyclic waves. This omega, though, is not equal to the square root of k over m, because this isn't a mass spring system. So it's got to be a little bit careful. This is dictated by other phenomena within the system. All right, so we got a good hold of what is k, what is omega. Like we've said, the phase constant is just a matter of how do we start things out in time. And the minus sign in front of the omega says that the wave traveling to the right. If it was plus, well, then it's traveling to the left. And that's it. All right, so what else can we do with this? Well, there's one other nice thing that we can do. And think about this. So if we go back to this scenario right here, and think about the wave speed or the wave velocity. We know it's traveling that way, so typically in one-dimensional aspects, we just call it the wave speed, and note that it's traveling to the right in this case. We could start figuring out what that is. How? Well, look at it. This is one full spatial cycle. This is a snapshot in time, right? Snapshot in time at t equals 0. Well, as time goes on, this wavelength right here is moving this way at this rate. So this particular section of the wave is progressing forward in time until, well not until, but there's a point in time in which it's moved forward by one full cycle spatially. Ooh, or one full cycle temporally, I should say. So after a period of t, the time it takes for one full cycle to be produced, this cycle spatially has to make room for the next cycle that's being produced. So this cycle here will move forward by one full wavelength and the time it takes to produce a new cycle. So that this point here is oscillated through one full cycle, you've got this specific segment again. So the big point with that is, and maybe a little confusing, is that the wave must advance forward by its wavelength over the time it takes for one complete cycle to be produced. That is, the wave has to be traveling at a rate over here. Let's do this. Traveling wave must advance forward by one wavelength in the time it takes to produce one cycle. We know that that's called the period, right? Time it takes to produce a cycle. So we have to have this. Moves forward by lambda in a time t. And what do we have? Well, if this is moving at a constant rate, which is the only kind of waves that we're looking at right now, nice even flow, cyclic, then we have coordinate of distance equals rate times time. So this ends up coming out to the distance that goes as lambda, the rate that it's traveling at is v, and the time is t. So we can take this and say that the wave speed v is equal to lambda divided by t, wavelength divided by the period. That is the wave speed of the wave. And because we have that lambda is equal to 2 pi divided by k, and omega is equal to 2 pi divided by t, we should be able to see that we can also write v in terms of omega and lambda. So omega and k. We'd have to switch this around, right? But we kind of see that. There we go. V is equal to omega divided by k. So if you've got a formal expression, a times the sine of kx minus omega t, you know what omega and you know what k are, you know what the wave speed is automatically, just by taking the ratio of omega to k. That's it. All right, so that's nice to be able to do. And it's the building blocks on which we will continue onward in describing wave characteristics. Important things again, wavelength related to wave number, period related to the angular frequency, and the wave speed, as well as the traveling to the left or right, plus or minus omega, and the amplitude of the wave, the maximum displacement from its equilibrium position from which everything is being measured, the displacements anyway. So everything's in one spot. We've got ourselves transverse traveling wave. I don't know, this is sinusoidal. Y of x and t is equal to a times the sine of kx. I'm going to put minus plus omega t plus v. And note that it's minus omega t traveling in plus x direction. And plus, so omega t if traveling in the minus x direction. Like I said, normally we're just going to say it's traveling to the right, but just to be thorough with that, this is what we got. A is the amplitude, measured in meters. SI unit is meters, and then we've got K is the wave number, and lambda is equal to the wavelength. From both of these, you've got the relation between the wave number and the wavelength. K is equal to 2 pi divided by lambda. Lambda is measured in meters, K is in radians per meter. So we've also got ourselves omega, angular frequency. Got it. T is the period of the wave. From these two, we've got the expression between them. Omega is equal to 2 pi over t. So we could put in these values up there, but generally we just have K and omega. That's great. So the last thing would be phi. Phase constant determined again by initial conditions. And oops, almost forgot the last one that we have written over there, but wave speed is equal to wave speed is equal to lambda over t, which is equivalent to omega over k. And SI units, meters per second. There we go. There's kind of the sum up of everything that we've done thus far, and didn't want to leave that hanging. It's nice to have it all in one place. All right, I'm going now. Now I'll wave bye. Bye.